Hi everyone, my name is Rangit Pan and I am presenting our work with my advisor Ritesh Rajan. Today I'm going to tell you about an approach to decompose convolutional neural network into modules to enable the reusability and replaceability. Before we discuss the decomposition of the convolutional neural network based models, we want to give a brief overview of how decomposition works in the traditional software development and the current state of the deep learning models. Exactly 50 years ago, David Parnas envisioned how decomposition and modular programming can help developing systems. In the seminal work on identifying criteria to decompose traditional software in modules, it has been mentioned that modular programming can help to build one module without the knowledge of other modules, and these decomposed modules can be reassembled or replaced to build a new system. First, monolithic software is a piece of code without components or pieces, whereas a decomposed software with components or pieces that can be utilized independently. And the process that decomposes a monolithic software into components or module is called decomposition. For instance, on the left-hand side, we have a code that performs basic mathematical operations. Decomposing the code will create modules for each mathematical operation that can be invoked as necessary. There are a number of benefits of decomposing software into modules, such as reusability, replaceability, independent testing, and independent development. In this work, we'll show the first two aspects of the decomposition. Now, in the current state, a deep learning model can broadly be built in two ways. First, building from scratch. However, if we want to change something in the model, we either have to train from scratch, that increases the cost and effort significantly, as training from scratch is always very expensive, or we can use transfer learning. In transfer learning, the process increases the complexity as the significant level of expertise is needed to do so, and decrease the scalability as only if the model structure matches this operation can be done. Now we'll discuss a real-world scenario where decomposing a model into modules can be beneficial to resolve an issue. We envision decomposing models into modules can help to solve real-world problems. For instance, in the past, Google Photo app tagged a black woman as a gorilla. Not only that, recently Facebook, currently known as Meta, has also made a similar instance, where a black man has been labeled as primate on the video. While we do not have the information about how Facebook or Meta resolved that issue, we found that to resolve the similar issue, Google has decided to remove the output class gorilla by suppressing the output level. In fact, they have suppressed the output for chimpanzee, monkey, chimp, etc. from the model that recognize a wide range of images, for example, car, human face, etc. Though the problem can be temporarily solved by suppressing the output level to fix the model, one needs to retrain the model to actually fix the problem. Now, suppose we can decompose a CNN model into modules, one for each output class. The module takes the same input as the model, but only tells whether the input belongs to the dominant output class of the module. For instance, a module for car-related images can only recognize an input as a car or not. Let's assume we can decompose the faulty CNN model into modules for each output class. Also, suppose we have another working model trained with the same or a subset of dataset with having the gorilla and person output levels. This latter model does not exhibit the behavior present in the faulty one. If we can decompose both models, we can replace the faulty gorilla module with the working gorilla module that does not exhibit the incorrect behavior. Now, instead of the previous solution, we can train a new model with the person and the gorilla classes and validate that the trained model does not demonstrate a faulty behavior. We decompose the newly trained model into two modules, gorilla and human face, and also decompose the faulty module uh, and replace the faulty gorilla module with the new decomposed gorilla module. Or even we can decompose the faulty model into modules and remove the gorilla module from the collection, which is exactly similar to what Google did to resolve the problem. Each solution that we propose has its own pros and cons and can be applied on the available resources and the need. To introduce the notion of decomposition, in our previous work published in ICSE'22, we proposed an approach to decompose the dense space deep neural networks into reusable and replaceable models. However, the prior work focused on dense space network and did not explore more complex set of deep learning techniques such as convolutional neural networks. The prior work relies on the dense architecture of the model, where nodes and edges, weights and bias have one-to-one relationship. In contrast, edges in CNN are shared among all the input and output nodes. Also, the prior work performed backtracking mechanism to decompose the module, which is only applicable to the dense space layers and not to the other layer, for example, convolutional, merge, etc., which are common in the convolutional neural network. To that end, we propose an approach to decompose convolutional neural network for image classification problems into modules, one for each output class. Our decomposition approach comprises of three steps: concern identification, tangling identification, and concern modularization. Our approach starts with the trained model. For instance, in this case, a model that recognizes images labeled as A to D. First, our approach identifies the section in the CNN that is responsible for a single output class. Since we remove the nodes and edges for all non-concern output classes, the identified section acts as a single class classifier. To add the notion of the negative output classes, we add a limited section of the input from the unconcerned output mod classes. Finally, we channel the concerns to create our models. In this context, we use the concern and unconcerned as terminology that represent the input belonging to the output class for which the module has been created, and all the other output classes respectively. For example, for module A, output class A is the concerned output class, and other output classes such as B, C, and D are the unconcerned classes. First, we perform concern identification. Concern identification involves identifying the section of the CNN model responsible for single output class. As a result of the process, we remove nodes and edges in the model. In traditional CNN models for image classification, both convolution and dense layers have the notion of nodes and edges. For dense layers, the concern section can be identified by updating or removing the edges connected to the nodes. In dense-based network, there is a one-to-one relationship between the edges connecting the nodes from different layers. For each edge, the originating and the incident nodes are unique except for bias, where the incident node is unique. The edge between the nodes are removed or updated based on the value associated with the nodes. In this process, we identify the nodes based on the assumption that ReLU has been used as an activation function. Since our work is focused on image-based classification model, ReLU is the most commonly used activation function in the for the hidden layers. In a convolutional layer, we identify the inactive section in the output nodes by using a mapping-based technique that stores the position of the node that are not part of the model. First, we store the weight and bias of all layers, then we identify the part of the convolution layer that are not used for a single output class. In concern module identification, a module is created based on identifying the nodes and edges for a single output class. Since all the nodes and edges related to the other output classes in the dataset have been removed, the module essentially characterizes any input as the concerned output class or behave as a single class classifier. To add the notion of the unconcerned output classes and be able to distinguish between the concerned and unconcerned output classes, we bring back some of the nodes and edges to the module. In tangling identification, a limited set of inputs belonging to the unconcerned output classes has been added and corresponding nodes and edges also been added. So far, we identified the section network that is responsible for the output class and added examples for unconcerned output classes. However, a module is still an in-class classification problem. We'll channel the output layers for each module to create that into a binary classification-based problem. Instead of having n nodes at the output layer, we'll have two nodes, concerned and unconcerned output node. That has been kept. For more details, please refer to our paper. Now, we will discuss the evaluation of our approach. We have used three datasets. First, CIFAR-10, a dataset that comprises 3D images of different objects. It has 10 output classes, and dataset is divided into training and testing dataset. Second, CIFAR-100, the dataset has 100 output classes. This is widely used to evaluate CNN-based studies due to the complexity of the dataset. Third one is ImageNet-200, also known as ImageNet-Tiny. The dataset is very popular and widely used for research purposes. This dataset comprises 200 types of images. To evaluate our approach, we build 9 different models. These models are trained with the state-of-the-art architecture, for example, ResNet with 20, 32, and 56 layers. The name of the CNN model has been represented as the dataset hyphen the name of the model. For example, for the CIFAR-10 dataset with ResNet-10, ResNet-20, the model referred as the CIFAR-10 ResNet-20. We answered 3 research questions. Does decomposition involve cost? How modules can be reused or replaced to build a new problem compared to training a model from scratch? And does reusing and replacing modules emit less CO2? First, modularity has traditionally associated with some loss of performance. Abstraction sometimes cost in performance. Hereby answering this research question, we want to find, does decomposing CNN model have performance cost also? If we find that decomposed modules are efficient, it tells that decomposition is not losing any performance. For each model, we decompose that into modules for each output classes. For instance, for CIFAR-10, a module that has been built for each output class, for example, airplane, automobile, bird, etc. Then to compute the compose accuracy, each input has been sent to all the modules and a voting-based decision has been taken to get the final decision. In this case, a very cute dog. We report the results for all 3 datasets And for each dataset, we have three models. We report the top 1 and top 5 accuracies of the models, as well as the composed accuracy. For the first research question, we find that the average cost of decomposing CNN model into modules is 1.77% and 0.85% for top 1 and top 5 accuracies, respectively. Overall, we found that for the first research question, does decomposing CNN model into module involve cost? We found there is a cost of decomposition, but that is trivial. For the second research question, how module reuse and replacement can be done compared to retraining a model from scratch, we found that for the intra-dataset reusability, where we take the modules that are decomposed from the models built using the same dataset, there is a gain of accuracy that is 2.5%. However, for the case of inter-dataset reusability, where we take the modules built from the decomposed from the models that are built using different dataset, there is an accuracy loss of 7.63%. For intra-dataset replaceability, where we replace a part of the model by a module built from a model from the same dataset, there is an accuracy of 0.02% for top 1 and 0.01% for top 5. For inter-dataset replaceability, where we replace a part of the model by a module decomposed from the model from different dataset, there is a gain in accuracy for top 1, but for top 5, we have a loss of 7.1%. For the third research question, does reusing and replacing the decomposed modules emit less CO2e? We found for all the cases, the composed models using these decomposed modules emit less CO2e compared to training a model from scratch. So how we can leverage the notion of decomposition to approach more research gaps? In the past, decomposition has benefited the traditional development process in various ways. We hope similar to that. Deep learning model development would similarly be benefited. For instance, in our prior work and this work, we show the possibilities of reusing and replacing the modules in various scenarios. While in traditional software, the decomposition-based approach provides insight to the inner workings of the software, we believe decomposed module can also provide more granular explanation of the deep learning models. Also, we hope that such modules built with different needs can help to ease the development and the maintenance process to make it more flexible and manageable. To the end, we propose an approach to decompose convolutional neural networks for image-based classification problems into modules, one for each output class. We show how real-world issues, such as issues that Google and Facebook and Meta faced earlier with incorrect classification, can be addressed by decomposing the model into modules instead of training from scratch. We discussed the methodology, a three-step process, taking the monolithic model as input. The output is a series of modules that is binary classifiers. We answered three research questions: the cost of decomposition, the possibilities of reusing and replacing the modules, and the consumption of CO2e in reusing these modules compared to the model trained from scratch. We made the preprint available where you can find more detailed descriptions of the paper.